Okay, so in the last class, we actually started the mathematical development of the swing equation, which is basically the classical representation of the dynamics of synchronous machine. So we came up to this point where we considered that we are representing the rotating body of the synchronous machine by some inertia J, and we were applying some mechanical input torque Tm at the shaft of the rotor, and consequently we were having some speed omega m at the rotor, and due to that rotation we had some generation of electromagnetic torque, which was represented by Te, and due to Lenz's law we saw that this Te, which is the output torque, electromagnetic torque, and this Tm, which is the input mechanical torque, they should oppose each other due to Lenz's law. Okay, just a minute, I have to attend the doorbell. Okay, just a minute, excuse me. Okay, sorry for the interruption. Okay, let's continue. So the dynamics of this rotating part of the synchronous machine was actually represented with the help of the Newton's law of motion. Okay, and we came up with this equation because on this rotating body having inertia J, we were having two different torques of one was the mechanical input torque Tm, and Te was in opposite direction of Tm. So Tm minus Te, this was the resultant force or resultant torque acting on this rotating body, and the right hand side was representing the acceleration multiplied by angular acceleration d square theta m by dt square multiplied by the J. So this is where we stopped in the last class. So today we will continue from here, and we'll look into a little more detail on this parameter theta m. Okay. So let's continue with that. So basically this theta m, this is the representation of the rotor angular position. Okay, so by this what is meant, if we look at some schematic of the rotor, let's say this is our rotor cross section, this is the stator, and in between you have some air gap. So these are the stator three-phase coils, and this is my rotor. Okay, and here you may have some coil, that is the DC field, and you will have some excitation. Let's say some IDC or VDC will be applied. And once you have this rotating body rotated with the help of the prime mover, you expect some output power out of these three-phase stator coils. So now can anyone tell what should be the rotor axis or the center of axis for the rotor? Considering it's a two-pole machine, let's say this is our north pole and this is our south pole, depending on this direction of current. So what should be the rotor position at this point? Or what should be the rotor axis at this point?
0 degrees, sir.
I'm talking about the, let's say, line which will represent some axis which will represent the rotor position. 0 degree. Okay.
180.
One. So you see there are difference in opinions. Okay. So basically, first of all, we have to, okay, it could be 0 degree, it could be 180 degree, it could be any other degrees. First of all, to measure a distance, we have to set a reference point, isn't it? Let's say you are talking about a car, position of a car. Okay, this is a car, and it is moving in this direction. And I say, what is the distance, or what is the position of the car? What is the distance of the car? So if it is asked that what is the distance of the car, of course, you should know what is the reference point of measuring the distance, right? So let's say if I talk about this frame, which is, let's say, a wall, stationary wall, fixed wall, then you can easily say, well, if I start from this point, the last end of the car, then this should be the distance, right? So let's say this is X, or let's say this is some theta. So when we talk about some positioning or height or distance or whatever, be it angular or linear, we have to have a reference point in our mind. Okay, otherwise you can't actually measure the distance or the height or any parameter, any such parameters, physical parameters. So first of all, let's, as we have fixed that this is the point from where we will measure the distance. Okay, so this is my reference point, and this is the point, this is the body, this is the location on the body of the car up to which we will measure the distance. Okay, we could have also chosen this point as the distance, right? But instead of that, we are choosing one point on the body of the car, one axis on the body of the car, and one reference. So we have to choose two things actually to measure a distance. Okay. Similarly, let's say this is the ground level. Okay, this is the ground level, and there is a person standing over here. So if you say, what is the distance of this person from the ground? So if you say what is the distance, it is better to specify, well, what is the distance of his head, or what is the distance of his, let's say, the mid part of the body or the arm or whatever, right? So depending on this position, this location, and the reference point, this distance will vary, right or not?
Yes, sir.
This distance will vary. This distance could be from here to here. Of course, we are fixing the reference, but we have to also fix some point on the body of this person so that we can have this measurement done correctly. So if we say the measurement is done from this reference up to the head, then this will be the height. If I say, well, up to the midpoint of the body, then this should be the height, and so on. So we have to fix two points. One is the reference point or the reference itself. Another one, some point on the body for which we are going for measurement. So similarly, we are going to fix two things there for measuring the rotor position. Okay. Number one, we have to fix a reference point as we did here. This was a reference point. Similarly, this was the reference point, the ground reference for measuring the height. So similarly, for measuring the rotor distance, we have to set a reference frame, okay? This is one thing. Another thing, we have to fix the rotor axis, okay? We have to fix some point on the rotor for which we are going for the measurement. So because it is a two-pole machine, usually what we do, we take the center of the axis, center of the magnetic field axis, okay? Center of the magnetic field axis. Why it is the center of the magnetic field axis? Because you see, when you excite the rotor coil with this DC field excitation, then this is the direction from which your flux will come out. And this is the direction through which your flux will get into the core again, back, right? So this line, the dotted line that I have drawn, this is basically your magnetic field axis or rotor field axis. So if I draw some imaginary line, this is basically the rotor axis we are interested on. So this is our rotor axis. And this is the axis which will signify the rotor position. Okay. So the rotor positioning has been fixed. One thing is fixed. What about the other thing? What about the reference frame? Well, the reference frame has to be chosen by us. Now there are two ways to set the reference frame. Let's again take the example of this moving car. Let's erase this for the time being. Now, as you know, the angular distance or the linear distance, it could be, or the velocity, there is a concept of absolute value and relative value, right? relative position, relative speed, or absolute position, absolute speed. So if I say I'm measuring the car distance, this is my car, this is the point of the car. If I'm measuring the car distance, okay, this point of the car from some stationary reference frame, this is a wall, okay, this is a wall, stationary, it's not moving at all. So the car is moving, of course, at some certain velocity. So if the reference is fixed, but the car is moving at a certain velocity, let's say some velocity omega s. So as time increases, what would happen to this theta?
Theta will also increase.
Theta will also increase. So if I try to plot it with respect to time, if I try to plot this theta with respect to time, because this is a constant speed, what would happen? Or if I take at t equals to 0, there was some certain theta. So let's start from here. So it will be a constant slope, right? Ever increasing distance. Clear? So this is if the reference frame is stationary. This will happen with theta. Okay. Now instead of this, if so this is known as the absolute position of the car. So when we measure with respect to some stationary frame, we call it absolute measurement. On the other hand, if we make this wall moving, if the wall itself is moving, then what will happen? Let's see. If the wall itself is moving, it's no more stationary. But now let's make it moving. So the frame itself, the reference itself is moving, the car is moving, and let's say the speed of their movement is same. Speed of the movement are same, exactly same. So what would happen to this theta with respect to time?
Remain same.
It will remain constant. So with respect to time, let's call this distance as something else, delta. Okay. So this is my delta now, not theta, just to differentiate between absolute measurement and relative measurement. So with some initial non-zero value of delta, this will remain constant. Okay. Is it clear? So,
yes.
So we will be using this linear, whatever I have discussed till now, this is for linear motion. So same thing is applicable for angular motion or angular speed. Okay. So because our rotor is moving in an angular manner. Okay, rotor is moving in an angular manner because there will be prime mover, and due to the movement of the prime mover, due to the torque of the prime mover, this rotor will keep on moving. So this rotor axis actually will move, right? This rotor axis will actually move because this rotor body will keep on moving with the help of the prime mover. So with this line, this rotor position actually means this rotor axis already mentioned. And this stationary reference frame is for measuring the rotor position in an absolute manner. Okay. So if we take a stationary reference frame for measuring the rotor position, you get whatever angle you get, whatever distance you get, that is absolute. Okay. So well, instead of that, if we take relative measurement, so before we go there, let's try to make a relation between this. So d theta over dt can be written as some omega. Okay, this will be absolute omega. This will be absolute omega because the theta itself is absolute. Theta means it is measured, it is the rotor position measured with respect to some fixed frame, stationary frame, as mentioned here, stationary reference frame. So whatever omega will be obtained, that will be some absolute omega, okay, not relative omega. So that will be absolute speed of the rotor. Now come to the next scenario where we will take relative measurement, okay, of the rotor position. So instead of the stationary frame, now we will take the rotating reference frame, and that is just because we want to have some relative measurement of rotor position as well as rotor speed. So we introduce another reference frame. This is our second reference frame. So this was the previous reference frame, like the fixed wall for the moving car. And this is a moving wall, you can say, okay, or moving reference frame. And the speed of the moving reference frame is intentionally selected as synchronous. When you say moving reference frame or rotating reference frame, you have to set some speed. So we intentionally set it at the steady state or equilibrium speed for the synchronous machine, which is synchronous speed. So we can say also that this also has a speed, but the speed of this reference is 0, right? Because it is stationary. So you can also set some speed, but that should be set to 0. And now you introduce one rotating reference frame, which is the synchronously rotating reference frame. And the rotor position, when it is measured with respect to this stationary reference frame, that is theta. That is this bigger angle theta here. However, if we measure the same rotor position with respect to some moving reference frame or rotating reference frame, we call it delta. And the rotor position is denoted by omega m. Sorry, the rotor speed. Sorry, the rotor speed is denoted by omega m, and the rotor position is denoted by theta m with respect to stationary reference frame. Omega ms, it is the speed of the stationary synchronously rotating reference frame. And delta m, it is also rotor position, but measured with respect to the rotating reference frame. So these are the descriptions of all these notations. Now, can we relate theta m and delta m? Is there any way to relate these two? Because one is absolute value, another one is relative position, relative value. So simply we can take help of this diagram over here. So we can simply write, if you see that this bigger angle over here is theta m, so theta m should be some delta m plus something else. And this omega ms into t, this is nothing but this gap. Okay. So omega ms is the speed of this frame. And after time t, it has moved this much of distance. Okay, this much of distance has been moved by this rotating reference frame after time t. So this gap is nothing but omega ms, which is the speed of the reference multiplied by time, which will give you some distance. Okay, equivalent value of angular distance. So omega ms t plus delta m will give you the theta m. This is how we can relate these two. So once we are done with this relationship between these two, next we would like to replace this d square theta m over dt square by the delta m, okay, corresponding delta m, or the relative position. Now, before I move forward, as we said earlier that d theta m, if I take d theta or d theta m over dt, we were supposed to get some absolute speed of the rotor. Now, if I take d delta m over dt, what should I get? Can anyone tell? Let's make it omega m. This expression will give you some absolute speed. This should give you some relative speed, because yeah, anyone? What should be this relative speed?
Theta ms.
Not theta ms.
Ms.
Theta ms. There is no theta ms. There is omega ms.
Omega ms.
Omega ms.
Minus.
Omega, yeah, Hasanuজ্জামান. This is relative,
Omega
right?
ms.
So
Omega ms.
either you
omega
write
m and
omega m minus omega ms, or you write omega ms minus omega m. This is relative speed. So there
So
should
omega minus omega ms.
there should be two different speeds. Okay. So you see, this is, you can also say this is relative speed, but now you can say simply this is omega m minus 0, because this also has a speed, as I said. We said this omega is 0, right? It has a speed, but it's a 0 speed. So we can also say it is also some sort of relative speed, but measured with respect to some 0 reference speed. Do you get the idea? But in this case, we are still measuring omega m, but now that is measured with respect to a reference which is moving at this speed. Okay. So d delta m over dt will give you some relative relation, and this also gives you, of course, relative relation, but however, this value is 0 here, as is shown over here. Any confusion about this?
No, sir.
No. Okay. So let's continue. So we have seen that, well, we can relate this theta m and delta m. We can have the derivatives calculated for this theta m and delta m. Now let's move on. So now if we differentiate, okay, now if we differentiate this one, so what do you get? Again, explicitly, if you differentiate this one without looking at this diagram, just for the time being, forget about this diagram, just differentiate this with respect to time. What do you get? D theta m over dt equals to omega ms plus d delta m over dt, right? So this is what you get. D theta m over dt equals to omega ms plus d delta m over dt. Now what is d theta m over dt? As I wrote earlier, d theta m over dt is nothing but, this is nothing but omega m. So we keep this omega ms, and we also keep this as it is. And then what we do, we simply write what is d delta m over dt. It is, so you can see, we can also get it in this way. This is already I mentioned. Okay, so d delta m over dt is nothing but some relative speed of the rotor. So that means this d delta m by dt will give you some non-zero value whenever you have this omega m and this omega ms unequal. Okay, when these two would be unequal, when the system is moving at a steady state equilibrium, okay, or at some equilibrium point, what should be the speed of the rotor at a steady state?
Synchronous speed.
Yeah, so omega m should be omega s, and that should be also, because your reference frame is also moving at synchronous speed, right? So at a steady state, you have omega m equals to omega s, and that is equal to omega ms. So basically, at a steady state, you don't have any d delta m over dt. So d delta m over dt would be 0 at a steady state. So this, you can also explain this thing in this manner. However, under dynamic situation or transient situation, omega m would be different from omega ms, and accordingly, you can expect some non-zero value of d delta m over dt. So that means there will be some changes in delta m value. Now, if we differentiate again with respect to time, so we can have a very clear relationship now. A direct relationship can be established between d theta m by dt and, sorry, theta m and delta m, their double derivative. If I calculate another derivative of this with respect to time, so you get d squared theta m over dt squared, and you simply take this portion over here. Okay. Take the double, you take another time derivative of this. So what do you get? What is omega ms? Is it a constant or
Constant,
a variable?
sir.
It is a constant. Excellent.
Constant.
So because this is a constant, if you take the time derivative again, so it will vanish, and ultimately this will become the second derivative. So you can see that they are directly related. Okay, d square theta m over dt squared equals to d square delta m by dt square. So in the second time derivative, they are exactly same. However, in the first time derivative, they have some difference. So we can simply replace Tm minus Te, which we had in our earlier slide, slide number 7. So now we will replace this d square theta m over dt square by d square delta m over dt square. So simply we replace it in the previous, on the first equation where we started from. Next, what we do, we multiply this equation on both sides by omega m. Why do we multiply by omega m? Because instead of torque, we would like to see the expression or see the value of the powers. Okay, so as you know, P equals to T omega. Okay, so the relation between power and torque. So probably this is how you write torque. So P equals to tau into omega. So we already have the expression in terms of torque. Now we want the same expression in terms of power. So simply we multiply both sides by omega m. So j omega m d square delta m by dt square equals to Pm minus P, using this relation over here. Next, what we do some little bit more manipulations. So we simply again multiply by half j omega ms on both sides. So half j omega ms multiplied on this side, half j omega ms multiplied on this side, and we divide the entire equation on both sides by the base MVA. Okay, we divide both sides by the base MVA. Just a minute, there was j omega ms, so probably there is a slight mistake, I have to correct it. So this should not be there. Okay, so we are actually multiplying not by half j omega ms, we are simply multiplying by half omega ms. So this is the additional term over here. We are multiplying half omega ms on both sides and dividing by SB. So there will be a correction, I will correct it, inshallah. So once you multiply and once you divide, why do we actually divide by SB? Because SB, that is the base MVA, base power. Remember, we are now dealing with power. We are no more in the torque domain. We are in the power domain. Okay. So these are the actual values of the power. If you want per unitization, okay, per unit representation, so you have to divide by the base power. Okay. And in AC system, the base power is usually taken in MVA. So SB is nothing but the base MVA for the system under consideration. And in the numerator, we do some manipulation. We'll see why next. Okay, why do we actually incorporate this half of omega ms? So next we define a new parameter, and we assume that there is a small assumption. We assume that omega m is approximately equal to omega ms. Okay. So here you see omega m multiplied by omega ms. And if the system is stable, of course, there is a condition. If the system is in the stable mode of operation, then you can say omega m, it actually doesn't go, even in the transient state, it doesn't go well beyond omega ms. Okay. It remains very close to omega ms. Okay. So for the stable case of the dynamic analysis, this omega m, which is the actual rotor speed, and this omega ms, which is the speed of the rotating reference frame, they are approximately equal. Okay. So considering this assumption, we can write this omega m multiplied by omega ms as omega ms squared. Then we have j half divided by SB. And this portion, what do you have at the top? What should be the unit of this? What is this? This is power, right? This is MVA, volt ampere, voltage multiplied by current, simply volt ampere. But what is this? half j omega ms squared? Is it power or energy or work or what? Anyone? What is actually j? Isn't it equivalent to the mass of the rotating body?
Half mv squared, this formula is come.
Yes, sir.
Yeah, excellent. So this is basically nothing but equivalent to half mv squared for the linear motion. For angular motion, this is simply half j omega squared, where omega is replaced. Omega is taking the place of v and j is taking the place of m. So what is this? What type of energy?
Kinetic energy.
This is kinetic energy. Excellent. So this is kinetic energy. So at the top, we have some sort of energy. At the bottom, we have some sort of power. Okay. So what is energy? The relation between energy and power? Energy can be also written as this: power into time. And this is SB, which is basically voltage multiplied by current, or MVA, whatever. And if you cancel out megawatt and MVA, because megawatt is nothing but VI cosine theta. Cosine theta is actually unitless. So ultimately, in megawatt, you can write voltage multiplied by current as a unit. Then VI and VI are cancelled out. So ultimately, you are left with second. Okay. So H is known as the per unit inertia constant. Okay. What is the name of H? It is per unit inertia constant. But although it is known as per unit, and as we know in per unitized system, these are actually unitless, or at best we can use per unit, PU, as their units. However, there is a little deviation from that concept, because here the unit for H is seconds. Okay. So it is per unit inertia constant, but measured in seconds. So actually, for having this half mv squared representation, we were introducing this half of omega here intentionally. Okay. So that we can have some sort of half mv squared sort of thing at the top. Okay. This is why we are actually introducing this half omega ms on both sides. And we are dividing by base MVA just to express the thing in per unit. So in summary, this H is known as per unit inertia constant, and the unit of H is in seconds. Okay. So with this assumption, what we have got this equation: H multiplied by d squared delta m over dt squared equals to half omega ms, and this is we are actually getting from here. So this whole thing actually giving us H. So H d squared delta m over dt squared equals to half omega ms multiplied by this thing. So this is what we have. And then we can see that PM, as I said earlier, that PM is the actual value of power, and we are dividing it by the base value of the power, AC base value. So we can replace this by PM per unit, and we can replace this one by PE per unit. Now we go for the next manipulation on this equation. Little bit more manipulation is required before we reach at the final stage of the swing equation. So next we see that this M, okay, the subscript M here and here, these are basically the representation of mechanical quantities. Okay, I hope we don't have any mechanical engineers there, right? In this course, all are from electrical background, right?
Yes, sir.
Okay, so that's why we also want to move away from mechanical domain to electrical domain. Okay, so let's see how we can do that. So because these two are mechanical quantities, now we will see how we can convert these mechanical quantities into corresponding electrical quantities, and thus we can make the whole expression into electrical domain. Okay, so let's see. So now let's try to relate this mechanical measurement and electrical measurement. Okay, so what's the difference between them. Whatever measurement we know till now are mostly actually we measure in the mechanical, or in the physical world, we measure in the mechanical domain. For example, let's say if you are measuring a circular path, okay, let's say this red circle represents your current location, and then we start moving through this dotted line. When you move 1/4 of this path, how much have you moved with respect to pi? This is a pure circular path. So if you move up to the 1/4 of the distance,
45 degree.
yeah, 45 degree or pi by 4, all the same. If you move another quarter, this is pi by 2 or 90 degree. If you move another quarter, this is 2 pi by 3, not 2 pi by 3. This is, let's say, how much? Yeah, probably 2 pi by 3, 270 degree. And this is your 2 pi by 3 or 3 pi by 2. 3 pi by 2, not 2 pi by 3. This is your twice pi. Okay. So whatever measurement we are making here, and that immediately comes to our mind, okay, immediately comes to our mind, this is the concept of mechanical measurement. Okay. So the mechanical measurement, if we try to relate with the electrical measurement, or if we try to differentiate with the electrical measurement, the mechanical measurement, it doesn't actually depend on the electrical flux direction, because it is a mechanical measurement. Physically, how much you are moving in real world, that is actually mechanical measurement. Now, it doesn't depend on the location and the number of magnetic poles. Okay, it doesn't depend on the number and location of magnetic poles. On the other hand, the electrical angle is purely dependent. Electrical measurement means we are trying to measure actually with respect to, we are trying to measure our position or position of an object, location of an object with respect to some magnetic flux lines. Okay, so electrical angle is absolutely dependent on magnetic flux direction. Mechanical measurement has nothing to do with the magnetic flux direction or magnetic poles or magnetic flux lines. So this is the summary. Now let's try to apply this information on the figures over here. So mechanical one is already mentioned. Okay, mechanical measurement, this is pi by 4, pi by 2, 3 pi by 2, and twice pi 90 degree. Oh, probably this is a mistake. Yeah, okay, we make it 120. This is pi by 4, pi by 2. So this is actually
pi by 4 to pi by 2 should be pi by 2, the first one.
Oh, sorry. Yes. That should be pi by 2. Sorry, I made a mistake. Sorry. So this is pi by 2. Now it's fine. Yeah, this is 180 degree. That's why I was confused. So this is pi by 2. This is 180 degree. This is pi. This is how much? Then this is
3 pi by 2.
3 pi by 2. Now it's okay. This is pi by 1. Okay. So we are done with that. Now we come over here. So now we consider, let's say our machine is a 2-pole machine. Okay, it's a 2-pole machine. So we have a north pole and a south pole, and the flux lines are coming out from the north pole and entering into the south pole. And this is the, let's say, the core, rotor core. Okay. And let's say we are sitting over here. So in the electrical measurement, what we say that from any north pole to south pole, of course, symmetric values, symmetric locations under north pole and south pole, these symmetric locations, difference between these symmetric locations. Let's say we talk about the center of the north pole as a reference point, and we try to measure this distance of the object when it comes up to this point, and we measure up to the center of the south pole. So this gives you pi, 1 pi movement. Okay, means it is completely out of phase. Okay, so in this diagram you can also see this. This is the peak. At the center of the north pole you have the peak flux density, and at the center of the south pole you have the opposite peak. So you see it's completely out of phase, and that is 180-degree travel in electrical domain. And if I move again from here to here, how much I travel? Another 180-degree, another phase shift, complete phase shift. So if I continued with that, so that means from here to here, this is again pi. Okay. So in summary, when I complete one complete cycle for a two-pole system, when I complete a complete cycle, full cycle, then for a two-pole system, the electrical distance is also 2 pi. Because here we are covering pi from north to south, and from south to north, again, we are covering another pi. So north to south gives you 1 pi coverage. South to north gives you another pi coverage. So for a two-pole system, you have covered twice pi. So for a two-pole system, what is the relation between theta m and theta e? If we say this is theta e, the electrical one is theta e, and the mechanical one is theta m. What is the relation for two-pole machine? When P is equals to 2, they are equal. Okay, they are equal. Now let's go forward and try to find out the relation for four-pole machine. So as we said, the mechanical measurement has nothing to do with the number of poles and locations of the poles. So the mechanical distance coverage will be still the same. Okay, still if you start from here, and if you cover up to this point, you have covered pi. And then if you continue from here up to this point, it is still twice pi. So theta m remains unchanged, irrespective of increment or decrement in the number of poles present in the system. But now let's look at the electrical angle measurement. So let's draw 4 poles, north, south, north, south. They will come in an alternative manner. And now let's start measuring the distance. How much will be this?
Pi by 2.
This is pi. Not mechanical measurement. This is electrical measurement, remember. So from north to south, we will cover how much? Electrically pi. We're not talking about mechanically anymore. Mechanically, we are done here. It's twice pi. Mechanically is done. But from north to south, electrical measurement gives me a pure phase shift, complete phase shift, right? So if this red dot comes directly under the influence, directly under the center influence of south, we have actually gone through a complete phase shift. That is pi. Okay.
Yes, sir.
From south to north, how much?
Again, pi.
Again pi. From north to south, again pi. From south to north, another pi. So how much is the total coverage?
4 pi.
4 pi. This is theta e. This is theta m. So how can we relate now? For p equals to
Time
2,
is equal to 2 theta e.
yeah. So if p equals to 4, theta m equals to 2 theta e. Now we can continue in this fashion, but it will only consume time. So let's actually generalize, try to generalize the relationship. So how can we generalize? We can see that, can we write over here 2 by 2? And we can write this 2 instead of 2. We can also write it 4 by 2, right? So this is 4 by 2. Still, it satisfies the relationship. So instead of 2 here, now we try to generalize. Simply write P. Okay. And simply write P. Is it okay? So you see, if I use this relationship, I can have a generalized relationship between theta m and theta e in terms of number of poles present in a machine. So this is the generalized relationship between the mechanical angle measurement and electrical angle measurement. Any question? Similar relationship could be found for omega and delta. Of course, you can continue with the number of poles. You can check this with, let's say, 6 poles and 8 poles and so on. Okay, you should come up to the same conclusion, same generalized conclusion. Any question? Shouldn't be any question.
No, sir.
No. So once we are done with this generalized relationship between theta m and theta e, we will use it in our previously derived expression, and now we will move into the electrical domain from the mechanical domain. So this is what we do. So conversion of mechanical to electrical yields the following. So you can write, actually we have dropped E here. You can also include one E here. Delta E equals P by 2 delta M, and omega S, you can also write omega ES, E for electrical, equals to P by 2 omega MS, where M is for mechanical. So using these two relation, we go back, if we go back here, so we will use it here, okay, here and here. So we'll no more use delta M, and we will no more use omega MS. So we'll replace them by corresponding delta and omega S. So delta M can be written as 2 delta over P, and omega MS can be written as 2 omega S over P. So this is what we have done on both sides. And then there will be some cancellation, 2 by P here and 2 by P here. Those will be cancelled out, and ultimately you will be left with this d square delta over dt square. Remember, this delta, you can also add some subscript E here, but it has to be understood that for now, from now on, this delta is the same as delta E. So we are in the electrical domain. Okay, we are not in the mechanical domain anymore. And omega S, it is also in the electrical domain by twice H. There will be some cancellation, 2 by P on both sides, and ultimately P, M and PE, they are in per unit. So this is the swing equation we were going after, starting from the last class. So this is the swing equation. What is the order of this equation?
Second order.
It's a second order equation. Okay, second order ordinary differential equations. Now, interestingly, any second order system, or in general, any nth order system, nth order ODE can be transformed into n first order ODE. Okay. So nth order, any nth order ODE can be transformed into n number of first order ODE. So because we have second order, so that means we can always get an equivalent representation of this second order ODE by using 2 first order ODE. Okay. Here for our system, n is 2. So any second order ODE system can be replaced by 2 number of first order ODE. Let's see how we can do that. So for doing that, first of all, what we do, what is actually, what is the physical meaning of this? Which parameter do you get out of this? Is it angular position or speed or acceleration or what?
Acceleration.
It is acceleration. Excellent. So this thing over here, we get actually some acceleration of the rotor. Okay. So as you know, acceleration is actually the double derivative of some position. What is the first derivative of position? First derivative of position.
Velocity.
Whatever we velocity, angular velocity. Okay. So whatever we have discussed till now, have you seen this before in today's lecture? There was some m probably, but for the time being, let's forget. Did we use this earlier before today?
Yes, sir.
Yes, sir.
What was that? What did we write?
Omega m minus omega s.
This was right, and this was delta m, right?
Yes, sir.
So all these quantities were actually in mechanical domain. So you can easily replace this into electrical, you can take this into electrical domain, this into electrical domain, this into electrical domain, and simply you can write d delta over dt should give me omega minus omega s. Considering you can also include some E here, but I'm not including actually E. Okay. This means without any E and without any M, this means all these are here electrical quantities. So this is one of our ODE now. Okay. Out of this, there's a second order ODE. We are looking for two first order ODEs. So this is one of the ODEs. Okay. What should be the second ODE? The second ODE can be simply written as this. If you take the time derivative of this again, what do you get? D square delta over dt square, right? So what can you write on this side? What is omega s? Is it a constant or a variable?
Constant.
It is a constant. What is omega? Constant or a variable?
Is it also constant?
If everything is constant, then there will be no meaning in life. There should be some
So
variable.
it's a variable.
This is variable. Remember omega m, this is the actual rotary speed. And omega is actually the electrical equivalent of omega m. Okay. So omega s, this is synchronous speed. This is fine. This is constant. But omega is not a constant. Okay. If both of them are constant, then actually you will never get any deviation here. Right. So omega is not a constant. Omega is some variable which represents the actual rotor velocity, actual rotor angular velocity. So we can write this as this, right? So from here, if I take the time derivative again on both sides, I will reach here. And this one, I can write this, can I? Because this is the same as this. Okay. Is it clear? So omega s over 2h multiplied by pm minus pe whole bracket. This is our second ODE. And this is our first ODE. So this is how we can transform this second order ODE into two first order ODEs using very simple calculation. So whatever I have said, this is actually discussed over here, shown over here. So we are done with this. We can have a single second order differential ODE system for representing the swing equation. This is one way. Another way, we can use these two. So that means this d square delta over dt square equals to omega s pm per unit minus p per unit is equivalent to saying that d delta over dt equals to omega minus omega s and d omega by dt equals to this. Okay. So next, what we will do, we'll have a quick look at the expression of PE. I will move through very quickly because don't have much time, and these are very simple, the thing that is going to come. And I would like to finish the review part for this course in today's lecture, and inshallah next lecture I will start some more advanced things. Okay, inshallah. So now let's try to look at this expression. What is PE? PE is the generated electrical output power, right? PM, what is PM? PM is the mechanical input power. From where do you get PM? From the, as I discussed in the first class, PM can be obtained, could be obtained from any sort of turbine mechanism, turbine governor mechanism. So now we are interested for the time being, what is PE? Okay, so let's see what is PE. How do you get the expression of PE? So for getting the expression of PE, we consider a simple network. This is the one line diagram where the generator, synchronous generator, is represented by this, a voltage source behind a transient reactance, JXD dash. So this is your generator itself. VG is the external voltage for the generator. What is the difference between VG and E dash? Can anyone tell? Or simply E, if I say this is E. What is the relation or what is the difference between these two? Could they be equal? In any case? So this is what I'm saying. This is VG. This is your VG. This is your JXD dash. This is your E. Now, do you remember something from your undergrad level? Synchronous machine, equivalent circuit.
This is the terminal voltage.
VG is the terminal voltage. Excellent. E
EMF that
is
is
the internally generated EMF. Okay, we call it internally generated EMF, or if you still ignore the armature reaction, then it is actually the open circuit voltage. Okay. When you consider the armature reaction, then there will be some drop from the open circuit voltage, and you will ultimately get the internally generated EMF. So this is E, and in transient state, we just include this single dash at the top as the superscript that represents the transient state for the machine. So VG is the external terminal for the generator, representation of the terminal voltage. When there is no load, of course, this E and VG would be exactly same, because there will be no armature resistive drop or armature reactive drop or no armature reaction under no load condition. So E will be exactly same as VG, otherwise not. And then we considered ZL. This is the transmission line reactance. And then this V is the infinite bus that we mentioned earlier in the first class. ZS is some local load connected at the external terminal of the generator. And these 1, 2, 3, 4, these are nothing but the bus number on the node numbers. And we are interested in calculating PE, which is being supplied by the generator to the infinite bus. Okay, so we're interested here. Remember, okay, yeah, we are interested here at this point. And of course, this generator will inject some current into this node, right? So the current flow into terminal number 3 or node number 3, let's say it is I. So these are voltage representation of the network with the voltage source. We can also replace the voltage sources with the equivalent current sources, right? So we can have the injection model instead of the voltage source model represented on the right side of this slide. We can also replace these voltage sources by the corresponding current sources. Okay. So in that case, the network would look like this after some manipulation. You see, you don't have node number 3 here on the left diagram. Okay. On the left side, you don't have node number 3. So what we have done here, first of all, we have removed the voltage sources and we have replaced them by the equivalent current sources. This is one thing. Then what we have done, we have transformed this T network into equivalent pi network. Where is the T? Can you find? So this is the T, or this is the Y. Okay. This is the T. Can you see? This is one arm of the T. This is the middle point of the T, and this is the right arm of the T. So it's like, you can say it's Y, or if you straighten up these things, then it's like a T. Okay. So it's Y or T, whatever, then you convert it into pi network. So you see, this is something like pi. This is the middle branch, and these are the two shunt branches. So this is how we can reach from this diagram to this diagram. Simply, what is our target? Our target is actually, we are getting rid of this node, intermediate node number 3. So you don't see any node number 3. And while doing that, of course, you have to get some manipulation here done for calculating the pi elements. This branch, and this branch. Of course, they would not be the same as this, and this. Okay. So you do the Y delta conversion, or actually for here, this is, yeah, from Y to delta or from Y to pi, whatever you say. You do the conversion done, and here are some formula to help you out. So when you apply this, remember, these are impedances. Okay, ZL, ZS, JXD, these are impedances. I'm writing this in terms of admittances. So if you, these are the after the conversion. Okay, so Y10 is actually here. So if you write Z10, simply what you have to do, if you write Z10, so you can write 1 upon Z10 is actually your Y10. Okay, 1 upon Z20 is actually your Y20, and so on. So the T network is in impedance terms. I have dropped one step here. So first of all, what you have to do, you have to get the pi network in terms of Z10, Z20, and Z12. And then you have to calculate the corresponding Ys just by inverting these things. Okay, nothing special. So these are the relations, corresponding relations from the branch, for the branch elements in the pi network. So now once we are done with this T to Y to delta conversion, so what we will do next, we'll simply apply KCL at the nodes, at node number 1 and 2. So in the node number 1, if we apply KCL, what do you get? This is your current injected at node number 1. So this is I1. We consider this to be I1. Remember, all these are phasors. Okay, all these are phasors. So that means they have some magnitude as well as some phase angles. So this is I1 injected. How much will be the current here? Anyone? Considering the voltage is E dash at this node, how much will be the current? Because I1 would be summation of this current and this current, right? Let's say this is I1 double dash and this is I1 dash. So what would be I1 dash? And what would be I1 double dash? Please, quickly, running out of time.
So just applying KCL, that means E minus 0 divided by Z10 for I1.
For I1, which one? There are two I1s now.
I1 prime.
I1 prime?
Yes, I1 prime you have right here, right over here.
Yeah, okay. What is the relation? Y E dash minus
0.
0. Excellent.
Yes.
Then multiplied or divide.
Yes. Z10 that you have right.
Actually, yeah, 1 0. Okay, between node 1 and 0. So you should read it at 1 0, not 10. Okay, it is 1 0.
Sorry, sir.
No problem. I'm just clarifying the things. So yeah, so we can also write it in terms of admittances because we have the information of admittances. So we can also write this. Okay, excellent. What about this? This is E dash minus V divided by Z12. And instead of writing this, you can also write it in terms of E dash minus V multiplied by Y12. Okay.
Yes, sir.
Multiplied by Y12. So this is what is done actually here. After doing this, include this here and just simply group them. Group the coefficients together. So Y10 plus Y12 E dash minus Y12 into V. This is what you will get. Similarly, I2. This is I2. This is your I2 double dash and this is I2 dash. You can also get the expression. Okay, simply using the KVL. Sorry. So once you are done, I'm not going through this because the same process as this. So once you are done with this, we will try to represent this I1 and I2 in matrix form. So these are your input for the system. So E dash and V, these are the inputs. I1 and I2, these are the dependent variables or outputs. So simply take out the coefficients from these two equations at the top. So what's the coefficient of E dash for I1? Y10 plus Y12. Coefficient of V is minus Y12, simply matrix vector multiplication. What is I2 and E prime relationship? Minus Y12. And with V and I2, this is the coefficient, Y20 plus Y12. Okay. And these are the branch elements. Remember, these are the branch admittances. Now, if I look into the Y bus matrix instead of the branch elements of this network, if I try to find out the Y bus matrix, do you remember Y bus matrix? From load flow analysis, you required to calculate Y bus for very big networks. It is a For this case, it is a very simple network. So what was the characteristics of Y bus? Its off diagonal elements were equal. Remember? Off diagonal elements was equal. Diagonal elements was simply the summation of the branch admittances at that node. So if you look at node number 1, what should be the Y11 element for the Y bus? 2 branches are there. So you simply add the branch admittances Y12 and Y10. So you see Y12 and Y10. The off diagonal elements, how do you calculate it? Simply take the negative of the branch admittance. Okay, so between node 1 and 2, in this branch, Y12 is the branch admittance. You take the negative of that, so you get the Y bus entry. Y21 should be the same as Y12. This is because of the characteristics of your Y bus matrix, bus admittance matrix. And Y22, node number 2, you have again 2 branches. Simply add the elements Y12 plus Y20. So you see Y12 plus Y20. So this is how you can get it. So once you are done with this, bus matrix representation, next simply we will try to calculate our power. Remember, we are looking for the power expression, real power expression. How do you calculate real power? It is simply VI conjugate. What is VI conjugate? It is basically the apparent power. So the apparent power or the volt ampere is simply S is what? VI conjugate in the phasor representation, phasor notation. All these are phasors. So what is the real part? P, we can also write it as P plus JQ. So real part of this, real part of this will basically give you P, right? So the real part of this expression will give you P. So that's why we are calculating P equals to real part of EI conjugate. That means at this point, at this node, this is my E, phasor E dash, and this is my current injected into the node. And the conjugate comes because of the formula. And I'm taking the real part because I'm looking for P value, not Q value. So then what we do, we simply split or write down the actual expression of E dash. What is E dash? E dash is magnitude of E. And let's say the angle of E we consider to be delta, some phase angle. The phase angle of E is delta. Now what is I1 conjugate? From where do you get I1 conjugate? This is I1, okay? So what is I1? I1 is Y11 E dash plus Y12 V. Now, when we take conjugate, what will change? So if I1 phasor is Y11 E dash plus Y12 into V, okay? All these are phasors, remember, all these are phasors. So you have to know basically, okay, first replace all these expressions by their corresponding, magnitudes and angles. So probably I will take, do you have class right at 9:15? Hello?
No, sir.
Sorry?
No, sir.
No, sir. Okay. Probably I will take 5 extra minutes, okay, with your permission, so that I can just finish it. Okay. Probably up to another 5, up to another maybe 9:20. I think by 9:20 I should be done. Do you permit for that or no?
Always.
Yes, sir.
Okay. Okay. Thank you. Thank you. So we just express all the phasors by their corresponding magnitudes and phase angles. Okay, first. Then E, what was E? E was basically E magnitude, and angle, we consider angle delta. This is theta 11 for Y11, the phase. And again, this Y12, this is magnitude. This is theta 12 multiplied by V, magnitude. V, we consider it to be the reference, so V is 0. So if this is I1, what should be I1 conjugate? Where, what should be the changes?
Only angle changes in angle.
Yeah, because these are polar representation. So simply the magnitudes will remain as it is. And you simply negate the angles, okay? Multiplied by E dash and so on, okay? And so on. So you change this angle to negative and this is 0. So you just leave with it. This is 0. So this is I1 conjugate and that is actually written over here. Okay. So you see Y11 angle is negated, E magnitude angle is negated, plus Y12 angle is negated, V magnitude angle is 0, so it is 0. So then you simply express this phasors with respect to the Euler's identity, okay? E to the power j theta, A to the power j theta is magnitude into the real part and the imaginary part, okay? The Euler's identity. Or you can say this is in polar representation, you are using the Cartesian or rectangular representation, all the same. So that means you have to multiply all these things. You have to multiply all these things, and then you have to convert the polar expressions into corresponding rectangular expressions, and you have to take the real part, and you have to drop out the imaginary parts. Okay, so there may be 2 steps maybe I have skipped, but it's very simple, straightforward. So once I take the real part after taking the Cartesian or rectangular representation of this phasor, of these phasors over here, I get this. Okay. And then we take another assumptions just to complete the derivation. We take some simple assumptions because in general, these assumptions are valid. Why? Because you see, what is Y11, Y12? And theta 11, theta 12. Okay. Y11, it is basically some sort of admittance present in the system, right? And theta 11 is the corresponding angle for that admittance. So when we say we have purely inductive circuits, what is the phase angle for the purely inductive circuits?
$90 degrees.
90 degrees. Excellent. So that is 90 degrees. Why we are actually so concerned about this assumption is because let's say you are designing a power system. This is what? This is, let's say, part of the transmission line. Okay, transmission line. Now as a designer, what would be your target? You are generating some power over here. Okay, this is your generating station. Let's say you are generating some power and you are supplying it to the, let's say this is load center, and this is your transmission line. Okay, so as a designer of the transmission line, what should you try to do? Let's say the transmission line is represented by a short line, which is represented by R plus JX. Okay, so let's say for the time being, we are not considering any shunt elements. Let's say simple series representation of the transmission line. So what would be your target as a designer of this line? Would you try to make R highest?
No, sir.
No. Why?
It will drop power.
Yeah, it will actually create much loss. So that's why we say that, well, for this design, R is very, very less kept. Of course, you can't make it 0 exactly, but you try to make it very, very less than X. If you can achieve that as a designer, then you are actually here, right? You are actually here. Your phase angles becomes the impedance angles, so the phase angles for the impedances becomes almost equals to 90 degrees. And same thing for this branch and this branch. So this is a valid assumption. Okay, this is what we generally do as a designer. We don't want the real power losses to be occurring through the lines while we are trying to transmit power from the generating station up to the load centers. So this is a valid assumption. So we take all these thetas equal to 90 degrees by considering purely inductive circuits. So what will happen then? Y12. Okay, so let's see. theta 11 and theta 12 becomes 90 degree. So what do you get here? Cosine 90. How much is it? How much is that?
Cos 90 equals 0.
Cosine 90 0. So you get rid of this. Theta 1 to 90. What do you get? Cosine some theta delta minus 90. It gives you sine delta, isn't it?
Yes, sir.
Cosine theta minus 90 gives you sine delta. So this becomes sine delta. This is E prime V, E prime V. Y12 magnitude. Y12 is simply now the imaginary part. Remember, Y is G plus JB, okay, in general, but we are not considering any real part of the impedances. So G, the conductance part, goes to 0. B is left. So B is simply 1 upon X12. So this is what we have done here. So Y12. So this is the part of the expression for PE, which is left over. So we take it here. P equals to E prime V Y12 cosine delta minus 90. Y12 is simply B12, and that is equal to 1 upon X12. And cosine delta minus 90 gives you sine delta. So this is basically the expression of power we are actually looking for. Okay, so this is how you represent PE, which is, as seen from here, is a function of the internally generated EMF, magnitude of that, the infinite bus voltage, magnitude of that, the reactance between my generating source and my load center, the infinite bus. This is the reactance between that. You see, this is E dash, this is V, and the reactance is this, okay, X12. The transfer, this is called as transfer reactance. And the sine delta. What is the delta here? Delta, remember, it is the angle difference or the phase angle of the phasor E with respect to the reference phasor V. Okay, so it's the phase angle of the internally generated voltage E dash with respect to the reference. So this is how you can represent your power. And if you plot it as a function of delta, simply you get this. Probably you have seen it in your undergrad course, so I'm not going to take much time over here. So simply this is your power angle curve, where in the y-axis you plot the power, real power out of the generator, and in the x-axis you simply put your delta. So this is PE versus delta in short, or in technical term you can call it power angle curve or power angle characteristics for synchronous machine. Okay, simply we have to take from the delta value, you have to take from 0 to pi. Okay, what would happen if I go beyond this? Can anyone tell? If I extend it, it will go like this and it will go like this. This is generation. What about these two? Because sine, I mean, from more than pi, sine function more than pi gives you negative value. Sine anything less than 0 up to a certain value gives you negative values. So this is generation. This is generating mood for synchronous machine. What about this?
Loss.
Motor.
Yeah, these are motor. Excellent. Not exactly loss, but here you are actually taking power. Okay. Or if you want to say you are supplying, then you are supplying negative power. That means if you are operating in these zones, you are in the motoring mood of operation. So because we are considering our machine to be synchronous generator for the time being, so we limit our operation between 0 and pi. Is it clear? And this is our point of zone of interest. Here, this is motoring. Here, this is motoring. So the same expression can be used for synchronous motor, but then you have to move from pi to twice pi, or from 0 to minus pi maybe. So that's it for today. So in today's lecture, what we have seen and what we have done is finally we have achieved the expression of the swing equation, and we have seen the expression of the real power that comes out from the synchronous machine. We have seen the dependency of the real power on system parameters like E prime, V, delta, and X. And we have also seen how to actually get this expression of PE. Okay. So inshallah, in the next class, Okay, so this is only the classical model or the second order model for the representation of synchronous machine, which will allow us to have a simple model for analyzing the system, for analyzing the dynamics of the machine. However, there are some assumptions as we discussed at the very beginning of the lecture for the swing equation. So slowly we will try to get rid of those assumptions in our future classes. Okay, and we will see how we can incorporate more practical things. So inshallah, from the next class, be ready to get some advanced knowledge. Okay, inshallah. Okay, any question for today's lecture or anything else? No question. Okay, then.
No.
Okay, then let me finish the class here. Okay, assalamu alaikum.
Walaikum assalam.
Assalamu alaikum.
Wa alaikum assalam.